In this video, I want to talk about power and energy and how they are related, and also how power and energy are related to voltage and current. So first, let's just go over the definition of power. Power is defined as the time rate of change of energy. Basically, the amount of energy that is being either expended or absorbed by a circuit element over time. So we define P to be power, W is the energy, and T is time. So the amount of energy that we either expend or absorb over a unit of time is called power. So let us quickly go over the distinction between expending energy or absorbing energy. So what type of circuit elements do you think expend energy or provide energy to our circuit? You probably guessed right. So let's say if you have a very simple circuit, an LED that is connected to a battery, right? So the battery is expending or providing energy while the LED is absorbing energy, right? So this is a very basic example. What about if you have a switching circuit that has some capacitors and inductors too? So probably, most likely, if we have a voltage source or a current source, they most likely expend energy or provide energy, while the capacitor and inductor, it depends, because capacitors and inductors, they can store energy, whether in terms of electric energy or magnetic energy, right? So since they can store energy, it is possible that they can provide energy as well, right? So as you can see, when we are working with very simple circuit, mostly resistive circuits, the resistors are absorbing energy while the voltage source or the current source are providing energy. But when the circuits become more complicated and we have capacitors and inductors may absorb energy at times, but also can provide energy too. So we will see later on how that works out. So for now, that is the definition of power. But now, what is the relationship between power and voltage and current, right? What is the relationship between the three of them? Do you remember we said that voltage is defined as the derivative of energy with respect to Q, or the electric charge. Also, we define the current to be the derivative of the electric charge with respect to time. So now, based on these two equations, do you think we can come up with an equation that shows the relationship between power, voltage, and current? So power is defined as the derivative of the energy with respect to time. This equation can be transformed into a subsequent equation which shows the derivative of energy with respect to the electric charge multiplied by the derivative of the electric charge with respect to time. So when we have this, you realize the derivative of energy with respect to the electric charge was defined as the voltage, and the derivative of the electric charge with respect to time was defined as the current. So now based on this, we get this very simple yet very powerful equation that shows the relationship between power and voltage and current at any given time. So at any given time, the power of an electric element, right, a circuit element, whatever that is, equals its voltage at that specific time multiplied by its current at that specific time. So this equation is very powerful, and based on this and based on the concept of passive sign convention, we can see how different elements are either producing energy or producing power to our system or absorbing power. So simply put, the power is the product of current in the element and the voltage across the element at any given time. So this is very important. At any given time. Because nobody says that the voltage and the current in our circuit or for the specific element are always fixed, right? But at any given time, if you multiply the voltage and the current, you get the value for the power for that time for that specific element. So now, how can we tell if a component is absorbing or providing power? So let's just go over this circuit first. So I just call this 1. So in circuit 1, as you can see, we have the current that goes through terminal 1 and comes out of terminal 2. So this is the reference direction for the current. Also, as you can see, voltage polarity is between terminal 1 and terminal 2. So terminal 1 is positive, terminal 2 is negative. So based on this and following the guideline from the passive sign convention, you can see that the current is moving through the terminals in the direction of the voltage drop. So you see if we have a drop in the voltage in this direction. So based on this, for the equations, we use the positive values for both current and the voltage. So if we do that, power equals voltage multiplied by current. So quickly should be pointed out that in this equation, we consider the generic voltage and the generic current, right? We don't consider their directions. If we want to consider the directions, right, we should follow the passive sign convention. So when we do that, what we realize is that P here is V multiplied by I. So the voltage drop from terminal 1 to terminal 2 multiplied by the current that goes through it. Assuming that both V and I are positive values, the value for P is going to be positive too. So in this case, if the power is positive, that means that you are delivering power to this circuit element. Let's just quickly go over a case where P equals negative V multiplied by I. So between the second figure and the first one, as you can see, the direction or the polarity of the voltage didn't change. We have positive and we have negative for terminal 1 and terminal 2 respectively. However, the direction of the current has changed. Because now the current is flowing through the terminals in the direction of the voltage increase based on the passive sign convention that we have, we use the variable with a negative sign. So think of it this way. If the head of the arrow is going through the positive, that means that in the equation for the power you don't have any negative sign. If the head of the arrow is going through the negative, then you should have this negative sign that represents the that appears in the value or in the equation for the power. So now, assuming that both voltage and current V and I are positive values, for this specific circuit, the value for power is going to be negative. And the value for power, if it's negative, that means that power is being extracted from this circuit element. Or in another word, the circuit element is providing power to your circuit. You can follow the same analogy for the third circuit and the fourth circuit too. Here you have the arrow to go through the negative side of the voltage. So because of that, the equation for power has a negative sign in front of it. On the other hand, here you have the arrow direction to be going through the positive side of the circuit element. So because of that, we have a positive sign in front of the equation for the power. So if the power is positive, that means that the power is being delivered to the circuit inside the box. If the power is negative, that means that the power is extracted from the circuit inside the box. One other thing that you should keep in mind is that the reference direction for the current and the reference polarity for the voltage, they don't necessarily talk about the values of these variables, right? So you can have, let's say, the direction of the current to go in this direction, right? Because at the beginning, when you want to solve the circuit, you assign some random directions for your current, right? After you solve it, you may see that, oh, the value for this current is calculated to be negative 5 amps, right? So that means that you have negative 5 amps going in this direction, or it means that you have 5 amps going on the opposite direction, right? So these equations, all of these four, don't say anything about the actual values of these variables, the voltage and the current. They are only defined based on the directions that you have specified here, right? When you have the actual values, you can plug it in, and then that is where you can see whether an element is delivering power to your circuit or is absorbing power from other components in your circuit. In this video, we learned how power can be calculated based on the equation that we have for energy. Also, we saw what is the relationship between power and voltage and current at any given time in our circuit and for any circuit element. And finally, we saw how we can come up with the positive and negative equations for power that can help us determine whether a circuit element is absorbing power or providing power at any given time.